physics faculty here, and the title of this talk is actually suggested by a friend, Saving Infants in Heartbeat. It actually should be called Saving Infants by Their Heartbeat, but nobody would understand what that means. So this guy, anybody recognize this guy? So, some might, and you know, the older people do. When Star Trek was on TV, there was a Dr. McCoy, and he had a device that was called a medical tricorder. And he would wave this around over the astronauts if they were injured or ill, and it would examine them, it would diagnose them, and I don't think it could fix them, but at least told them what was wrong with them. Well, we're going to talk about electronic detection, maybe even diagnosis of the health and illness of premature infants. I think we will be better. That's better?
Yes.
Okay. So here's a premature baby in there's the incubator. The baby's all wired up, and all sorts of electronic information is coming out of that baby, or rather, all sorts of electronic data is coming out of that baby. But is there any information in that data? Well, you've been in hospitals and you have seen electrocardiograms. Each of those is a heartbeat. The electrocardiogram is analyzed and is given they extract the heart rate from it, and this baby's heart rate is reasonably constant at about 173, roughly 3 beats per second, typical of babies of that age. This is called the chest impedance. I'll tell you a little bit more about that later, but what it's measuring is breathing. Baby inhale, exhale. Then baby is doing something quite unusual because he stops. And then inhale, exhale, stop, breathe, stop, breathe, stop. It tends to have about a 15-second cycle. It's called periodic breathing. It should be called periodic apneas, but they call it periodic breathing. Baby breathes in these regular intervals. Very interesting from a dynamical point of view and interesting from a clinical point of view. Also, they measure the oxygen saturation of the blood. Using the finger or the toe, well, arterial blood is red. When you cut yourself, blood gets out into the air. It takes up oxygen from the air, turns red. Venous blood is blue, as you see there. Look at your own veins. You'll see that that's blue. Somewhere in your wrist, sometimes I can find an artery, and it's much redder. Anyway, what they do is measure the color of the blood and use that to determine how much of the hemoglobin is saturated with oxygen. And so that's what's being measured here. When the baby stops breathing, the oxygen saturation drops. And so that's having a regular rhythm there too. Interesting phenomenon in this baby. Well, this is a big data talk, and we have lots of data. Information like this has been collected. All these waveforms, everything that can be collected electronically, has been digitized and saved at University of Virginia, their NICU, Neonatal Intensive Care Unit, from starting in January 2009. And they are still transferring data to us. This is on Cyclone. All the waveform and vital sign data from the electronic monitors. They have 45 beds in their NICU, and the waveforms include the electrocardiogram, chest impedance, and the oxidation. Vital signs are things that are collected every 2 seconds. They're average things like the heart rate and the respiration rate, oxygen saturation. Well, there's 2 oxygen saturation signals. One is collected at 60 hertz and it oscillates with a heartbeat. The other is collected or analyzed every 2 seconds and saved. So it's about 10 terabytes of data. That's pretty big. That's, as far as I know, the biggest data set here at William & Mary. It's about 200 baby years of data. So everything, this signal has to be collected at 240 hertz, 240 numbers per second. Others of them vary more slowly and can be collected more slowly. But anyway, it's a lot of data. They have about 2,600 admissions over the past 5 years. More than 700 VLBW, but that's very low birth weight. Very low birth weight means less than less than 1.5 kilograms, which is less than about 3 pounds. Those are very, very small and very vulnerable babies. They also stored monitor alarms, and they created a connected clinical database. They put in related information about any respiratory support that the baby is on. They may have mechanical ventilators. They may have CPAP, continuous positive airway pressure, or they might be on room air. They recorded whether the baby was given medications, caffeine, including caffeine, for example, which is, or antibiotics. Were there major clinical events like surgery or anything like that? There's also a second database that I'll tell you a little bit about, and that has only heart rates. That's a much smaller database, but it has 3 billion heart rates of 3 billion heartbeats, the times of 3 billion heartbeats for 3,000 infants, plus clinical records of bacterial infections, of sepsis. And I'll tell you what we use those for. Overview. Medical issues are neonatal sepsis and apnea of prematurity. The observations are the ones I've told you. Electronic monitoring of the heart and the respiration. They all sound like medical issues. What can we quantitative folks contribute? Well, we're good at statistical measures, but in fact, medical people are really good at statistical measures because they have to be. Medical researchers anyway. We're good at signal analysis, we're good at pattern recognition methods, and we love, especially in physics, we love dynamical theories, and sometimes we're able to develop dynamical theories that describe what's going on. These are some of the people that we work with. There's a big group at University of Virginia. The leader of the group was Randall Moorman in the center. Abby Flower is the person who got me into it. She'd been a student here, did a senior project with me, studying the hydrogen atom. And then she went off and did some other things and ended up in this group and sent me an email at one point and said, wouldn't you like to get interested in this project? And like a fool, I said, yes, of course. And I've been having a wonderful time ever since. What's sepsis? Sepsis is presence of bacteria or virus or fungus or other organisms in the blood or other tissues, and the associated toxins that are associated with the invasion. Of 4 million births each year, 56,000 of them, that's in the US, 56,000 of them are very low birth weight, less than 1.5 kilograms. And for them, the risk of sepsis is high. Maybe 25 to 40% of all those babies come down with a major septic event. There's significant mortality associated with that, doubled risk of death for them, and increased length of NICU stay, lots of issues. And of course, today we put in high cost as well. The diagnosis of neonatal sepsis is difficult, and worst of all, it has a high rate of false negatives. How do they diagnose it? They take a little blood. Now, these babies don't have a lot of blood. They can't take very much. They take a little bit of blood and ask, is there something growing in the blood? And experiments determine that they often, when the baby actually has an infection, it often is not found. There may be as much as 30% rate of false negatives, rate of baby, well, they got this when babies later died, and they did a postmortem, found that the baby had an infection, but it was not found in the blood test. So, physicians administer antibiotics early and often. Question: can heart rate monitoring give early warning of sepsis? The idea is that the invading organisms, or else the immune response, might affect the pacemaking system of the heart, just as it affects all the other cells of the body. We have a pacemaker in our hearts, a small number of cells that set the rhythm of the heart. And if either the invading organisms or the immune response affect that pacemaker, maybe we'll be able to see it. And that was Randall's idea that got this whole thing started. Does the heart rate give a warning of illness? Well, here is two signals from two different babies. This baby has a heart that's ticking like a clock. This is time between beats, 350 milliseconds. And this baby, the rate hardly changes over this period of time. This period of time is about 20 minutes or so. Here's another baby. When we look at the time between beats, it's fluctuating all over the place. Looks like a graph of a stock market. Which is the healthy baby?
One on the right.
The one on the right. How'd you know?
Because it looks crazy.
It looks crazy. And babies are crazy. Well, you're right. I wouldn't have asked, of course. Many people sort of instinctively point to this one and say, look, hearts are supposed to be regular. But in fact, our hearts are constantly responding to all sorts of inputs. Inhale, heart rate goes up. You can check this with your own pulse. Inhale, heart rate goes up. Exhale, heart rate goes down. Wave your arms around. Think about exciting things. Heart rates will always be changing. And it was already known that people who've had a heart attack, some of them carry around with them what are called Holter monitors that are constantly monitoring the heart. And it was found that people whose hearts are not recovering from that heart attack, often the heart cannot change, cannot respond to all these inputs. A healthy heart can respond to all those inputs. Well, so Randall had the idea maybe something like this could apply for the babies also. Now, the babies have very healthy hearts. They've never been smoking, no cholesterol load yet, and so their hearts are healthy. Almost all their hearts are healthy. But they're subject to all sorts of other things, and including bacterial infections, and perhaps we'll see a signal in the heart rate. Here's a second warning sign. This baby's heart the rate is fluctuating a lot, but it's fluctuating in this very regular way. It's not like this kind of looks random. And in fact, what's happening is the baby's heart has sort of a level background, and then it slows down and picks up again. Slows down, picks up again. Slows down, picks up again. Physicists would call it a deceleration followed by an acceleration. They just call it a deceleration. The heart slows down. And in this case, in a very rhythmic way. Well, that also turns out to be a warning sign. Here's one example. Here's one baby who had a septic event, and this is now the heart rate. I've usually been showing you time between beats, but here we're looking at the heart rate. And the top curve shows 150 hours before that sepsis event, and heart rate is fluctuating all over the place. Looks like a healthy kid. 6 hours before that event, we're seeing reduced variability. There's sort of a pretty clear baseline there. And we're seeing some decelerations. 3 hours before the event, lots of decelerations. Well, then, okay, 3 hours later, that baby was recognized to be ill. That's just one example. Well, how can we see these things? They started with statistical measures. They looked at, for example, how do you measure the width of fluctuations? Use a standard deviation. So, use a standard deviation over some period of time, and look at the histogram. How frequently does a particular value of time between beats show up? And in this case, there's first of all broad distribution and a reasonably symmetric distribution. There's many small accelerations, many small decelerations. Here, one of the things that you'd be able to see if the heart goes to a nearly constant rate, this picture will get much narrower. And here, in this case, where there's there's few accelerations, you can see a sort of baseline, many large decelerations, then the histogram will look like this. It will be skewed off to the right. Okay, so they put in measures like this. They put in many other measures also, but they found that the standard deviation and the asymmetry turned out to be very important. There's one other quantity called sample entropy that I don't have time to tell you about, but also turned out to be a warning sign. And what they did is find the correlation of those measures with illness. What's the relationship between, well, any measures of the heart rate and illness? What they did, they report the correlation as fold increase of risk of sepsis. What they did, take any random moment, examine a window of 24 hours around that moment. Now, on average, in the first study, about 2% of the infants had a sepsis event in that 24-hour window. Now examine the heart rate characteristics in the days before sepsis and ask, how do they differ? Convert those differences into a risk factor. A 5-fold increase of risk of sepsis means about 10% of the infants. It's 2% on average. If you don't know anything, 1 out of 40, 1 out of 50 babies will get ill in the next 24 hours. 5-fold increase of risk of sepsis tells us that 10% of the infants showing those heart rate characteristics had a sepsis event in that 24-hour window. Okay, you can see that by looking back, but then you also have to look forward and see whether this holds up. They got together with a company called Medical Predictive Sciences Corporation, and they developed in their marketing a system for heart rate characteristic monitoring in NICUs. There's a computer beside each NICU bed, continuously collects the electrocardiogram, it extracts times of those peaks, tracks the time between peaks, and then provides the following heart rate observation that they call HERO. They're good at names like this. The system is installed in several NICUs in the US. A large randomized clinical trial is now complete. Here's the output of the HERO monitor. First of all, one just sees the electrocardiogram over here, and here's the individual pulses of the heart. Then there's a slider, and this slider can go back in time. The slider is set at this point for October 23rd at 2:30 in the morning. And here we see from 2 o'clock to 2:30, here is the heart rate in beats per minute. Okay, somewhere around 160 or so, 3 beats per second. That's normal for these babies. And reasonable fluctuations for that time, but then getting to be pretty constant here. And lots of large decelerations. And then getting to be very flat again, number of decelerations again. Okay, well, that's what was happening during that half-hour period. Let's look over a longer period of time. Here is the heart rate, the HERO number. If the HERO number is 1, that baby looks like an ordinary baby. Based on the heart rate, this baby is no more likely and no less likely to come down with a sepsis event in the next 24 hours. That baby is the average baby. Okay, so this baby, the numbers decreased, looked like the baby is quite healthy, went back up to 1, and then on the 22nd of October, the number went up to 2. That baby is twice as likely as the average baby to have a sepsis event in the next 24 hours. On the 23rd of October, it went up to 4. That baby is 4 times more likely than the average. And indeed, 8:30 that morning, blood test was taken, and the baby was, in fact, ill. Well, that was one baby again. Here's a few hundred babies. All these babies had a septic event. The septic event was set at time equals 0. That's when it was discovered. And they They looked at they compared the average heart rate index before and after that time with a clinical score, which took into account the things that nurses and clinical staff are normally using. Temperature instability is a warning sign, of course. We get fevers. The babies might get cold instead. Is the baby feeding well? Is the baby lethargic? The normal kinds of things that people would look at in the NICU. And they converted that to a quantitative clinical score. Remarkably, the clinical score and the heart rate index tracked each other very well until shortly before the sepsis event, and the heart rate index rose. This baby is having increased risk of a septic event, and the stars means statistically significant difference from the previous values. And so the score is rising, and notice that that's rising 24 hours, begins to rise 24 hours before any other clinical signs are noticed. So, infections go very fast in these babies. 24 hours warning is a wonderful thing. First conclusion, new quantitative analysis of non-invasive, electronically measured heart rate characteristics, standard deviation, asymmetry, sample entropy, provides an early non-invasive warning of sepsis events. They then went to a randomized clinical trial. This is what you have to do to prove that any new method is actually working. They got 3,000 babies involved, 3,000 very low birth weight babies involved in this clinical trial. They had a sample and a control. In the sample, they displayed the HERO score. They decided that the HERO score is a risk score. It doesn't say this baby is sick. It says this baby is more likely than the average baby to come down with a sepsis event. So they thought they better not tell the clinicians what to do. Just give them this warning and let them decide. The control, they saved the HERO data, but they didn't display it. Okay, so what happened in the control group? Out of this approximately 3,000 very low birth weight babies, there were 152 deaths. 1,489 babies in the control group, 152 deaths, that's 10%. Well, they don't all make it. ELBW means extremely low birth weight, and there were 100, of these 152, 133 of them were in that group. Extremely low birth weight means less than a kilogram. 17% death rate in that group. Okay, what did the HERO system do? Reduce deaths from 152 to 122, 10% down to 8%. That is 2% absolute reduction in the death rate, 22% relative reduction from 10 down to 8. And p-value, for those who've had statistics towards 0.04, less than 0.05 is considered the requirement for truth. In the extremely low birth weight babies, from 133 deaths down to 100 deaths, 17% down to 13%, and so a 4% absolute or 33% relative reduction. Go ahead.
Yeah, are those deaths from sepsis only or from
Mostly.
Okay.
Mostly.
Gotcha.
Second conclusion. This new quantitative analysis of these signals saves lives. Well, new question, and this is where we got into it. Would quantitative measures of decelerations provide additional information? And there's a nice problem in pattern recognition. Nice job for a physicist. That's what Abby Flower thought about doing, and we talked about it together and devised a method. Well, if you were told that you want to pick out, from a signal that looks like this, you want to pick out the big decelerations, teach the computer to do what your eye does. Well, you'd think about it a while and you'd figure out a way to do it. We want to decompose that signal into these big decelerations and a fluctuating background. There's a method that's called wavelet theory that you can choose more or less any pattern that you want and put in the pattern, and it will carry that pattern through the signal, digitally carry the pattern through the signal, look for matches, and identify the height of the match, and it can adjust the width of the match also. So you see that there's a fairly wide deceleration, there's a narrower deceleration, and there are programs for doing this. So then, each 20-minute segment of the signal can be characterized by its deceleration information, a number, location, width, and so on, and then we can examine the correlation of those metrics with illness. And the result, storms of decelerations are highly predictive of sepsis. If in a 4,000 beat record, that's about 20 minutes, there are 8 decelerations, that baby is 10 times more likely than the average baby to come down with a sepsis event in the next 24 hours. The deceleration measure is correlated with the statistical measures, but is also providing independent information. And you see that at least part of the time it rises ahead of the other statistical measures. So it is giving additional information, and counting and measuring decelerations gives a second method for early warning of sepsis. Now, an important finding here that couldn't have been known ahead of time is that heart rate decelerations are surprisingly similar in infants. We couldn't use a pattern recognition method, but for the fact that there's always that same shape, or, well, not always, but that same shape is very common. Well, what will we do in the future? Can we even diagnose the infectious disease? That is to say, can we identify the invading organisms by heart rate monitoring? We have preliminary evidence, and I've been wanting to finish this up for a long time and haven't been able to do it, but we have preliminary evidence that reduced variability in clusters of decelerations correspond to invasions by 2 different families of bacteria. They're called gram-positive and gram-negative, and what that means is that it's how they have different cell wall structures, and gram-positive, how they absorb a dye. A gram-positive bacterium will turn purple under a certain dye. A gram-negative bacterium will not, but it will turn, I think it's brown under a different dye. Okay, well, it looks like reduced variability corresponds to gram-positive infections, clusters of decelerations to gram-negative infections. Why is that important? Well, here's some of the names, strep and staph, or E. coli, or Pseudomonas. Why is that important? Because those bacteria respond to different antibiotics. So, if it's a preliminary result, but if it holds up, then we have the first example of continuous, non-invasive, purely electronic monitoring that not only gives early warning of infectious disease, but even gives a partial diagnosis and thereby identifies the recommended therapy. We have a medical tricord. Okay, discovery. We saw something I've shown you before, that within extended clusters of deceleration, sometimes there's a remarkable periodicity. And here, the heart rate is varying in this very periodic fashion. Well, show that to a physicist, and the physicist says, wow, I've found a harmonic oscillator there. And we can say there's something dynamical going on there. And in fact, for 6 different infants, periodicity was maintained for at least 10 minutes, in fact, longer. That's a very strict definition of periodicity. And in those cases, the time to the next deceleration was always about 15 seconds. Here's time between decelerations, never less than 10, never more than 25. And yes, it fluctuates, but always somewhere around 15. Okay, so we're seeing something physiological, but what is it? What is it that causes periodic decelerations? Well, we had various possibilities that we examined, and what we now are reasonably sure is that these are periodic apneas, very much like the things that I showed you in that first slide. So that leads us to this second topic, which is apnea of prematurity. Apnea just means cessation of breathing. It's very common in premature infants. In the very low birth weight category, more than half the babies. In the extremely low birth weight category, almost all babies have apnea very commonly. Thus, for no apparent reason, they'll just stop breathing. Well, for all of us, our breathing is very irregular. The heart has its own pacemaker, but the diaphragm does not. The pacemaker for the diaphragm is in the brainstem. And in fact, Christopher Del Negro over in Applied Science is learning how that those particularly specialized cells in the brainstem set a rhythm for the diaphragm. Well, okay, so we breathe in a very irregular way. What do we call a clinical apnea? For the babies, if the baby stops breathing for 20 seconds, that's called an apnea event. The nurses are supposed to record it. If the baby stops breathing for 10 seconds and the heart slows down and oxygen desaturates, then again, that's an event and they're supposed to record it. 3 types of apnea are common. Obstructive apnea is the kind that older people get. It's blockage of the airway. As people age, the tissues in the back of the throat get quite soft, and when they inhale, it's low pressure in the throat, and the throat can be blocked. Well, the babies get that too. Central apnea is the more serious because it's a cessation of respiratory drive. The brainstem simply isn't sending the signals to tell the baby to breathe. There are also mixed apneas where obstructive changes to central or vice versa. Central apnea is taken to indicate immaturity of the control system for respiration. And it may be a cause or an effect or a warning of other clinical illnesses, including sepsis. Anyway, it's a serious clinical event that requires immediate medical attention. We got it. We're not supposed to stop breathing. But the current generation of apnea monitors is unsatisfactory. How is, can you see over this? Is this in the way?
No, I can see.
Okay. How is the breathing measured? I already mentioned chest impedance. Well, the same leads that measure the EKG, they put a small high